In this video, we are going to learn how to find the domain and range graphically and algebraically. Let's look at example 6. What's the domain for the first function here? The domain refers to all the x values that this blue graph can take. So when you think of the domain, you think of the horizontal axis here. So what section of the horizontal axis or the x-axis did this graph take? So basically, you're just looking at where does the graph go from left to right. So going from left to right, it looks like it goes from the value -3. So it starts from here. As the graph moves to the right, it takes all the values that goes to the right on the x-axis, and that is all the way to infinity. So the domain here should be from -3 to infinity. Furthermore, you see this open circle here. That means the endpoint is not included. So for -3, we are going to use parentheses. And for infinity, we'll always use parentheses. Similarly, we can determine the domain for the second graph by looking at how it behaves from left to right. So let's think of this parabola in 3 sections. So from here, from 0 all the way to the left here, as you can see that the graph goes toward the left forever. Now I know you look at this as it's going down, but we have to disregard that direction when we're looking at the domain. When we talk about the domain, we only refers to left or right. So it goes to the left forever. That means it takes all the x values that goes all the way to -infinity. And then we have this section, which means that it takes all the x values that goes from 0 to 4. And then from 4, it goes to the right forever, which means that it will take all the x values that goes to +infinity. So at the end, the domain should be from -infinity to +infinity. Now let's see how we can find the domain algebraically. Let's say a graph is not present. How can we find it algebraically? Definitely. There are 2 restrictions that you need to remember. One is we want to exclude any value of x that makes the denominator 0. We all know that in a fraction, we do not want a 0 in the denominator simply because we can't divide by 0. The second thing you need to worry about, the second restriction, is we want to exclude all value of x that makes the radicand negative within an even index root. Now, let's recall some terminology here. Let's say we have a square root. Whatever is inside of this root here, that's called the radicand. And because this is a square root, the index is 2. If it was a cube root, then the index is equal to 3. So the restrictions really apply for an even index, like square root, fourth root, sixth root, and so on. There should be no restrictions for a cube root. So let's look at this example. There are 3 of them. So find the domain. Part A, we have a fraction. In fact, this is a rational function. Now, based on the first restriction, we want to exclude value of x that makes the denominator 0. Well, what happens if the denominator is 0? So 2x minus 5 is equal to 0. Then 2x is equal to 5, and x is equal to 5 over 2. We solve for x. So this x equals 5 over 2 here is the value that makes the denominator 0, which is what we want to avoid because we don't want the denominator to be 0. So x cannot be 5 over 2. So the domain could be any number but 5 over 2. If you look at the number line, it would look like this. So 5 over 2 in the middle. We want to exclude 5 over 2, but that's it. So that means we accept everything else, anything to the right of 5 over 2 and anything to the left of 5 over 2. So when we write an interval for this domain, you write two intervals, one going from negative infinity to 5 over 2, and the other one will go from 5 over 2 to infinity. We use parentheses for both 5 over 2's because we do not want to include 5 over 2 in the domain. Part B, h of t is equal to square root of 2 minus t. So that would be the second restriction. So the index here is an even index. It's a square root. You can imagine the invisible 2 there. We want the radicand to be non-negative at all times. So basically what it means is the radicand can never be negative. So we want to exclude values of x that makes the radicand negative. So 2 minus t here is the radicand. We don't want it to be negative, so we're going to set it equal to greater than or equal to 0. Negative means it's less than 0, and we don't want that. Solve this inequality. First, you subtract 2 from both sides, negative t on the left and negative 2 on the right. We still need to get t by itself, so we're going to divide both sides by negative 1. So on the left, we end up with positive t because two negatives make a positive. On the right, we end up with positive 2. Because we're dividing both sides by a negative number, we must reverse the inequality sign to t is less than or equal to 2. This right here is the domain. So when you write this, it's helpful to draw the graph. So here's 2, t is less than or equal to 2, which means anything to the left of 2, and we want to include 2, so we should use a bracket here. So the domain expressed in interval notation would be negative infinity to 2 with the bracket. Last but not least, we have p of x is equal to 2x squared plus 3x. Now, this one doesn't have a fraction, and it also doesn't have any kind of root, no radicals. So therefore, there should be no restrictions. So no restriction. Therefore, the domain would be all real numbers or negative infinity to positive infinity.